our next speaker is Dr. John Tamir. He's an assistant professor in the Chandra Family Department of Electrical and Computer Engineering at the University of Texas at Austin. He received his PhD from UC Berkeley in 2018. He has been working on MR acquisition and image reconstruction for 10 years and has contributed to the BART toolbox since 2015. So his talk is about reproducible MRI reconstruction with BART.
Thank you, Dan, and thanks everyone who's attending. So my talk's going to be a little bit different. It's going to be more of a live demo, and I'm going to paste right now in the chat a link to the landing page, which is a GitHub page, and then I'll share my screen and talk a little bit about BART and then go into the demo where we do some reconstructions. Okay, so sharing my screen now. So if you go to the link that I just posted, it'll take you into this folder, which is the landing page for today's tutorial. And it just consists of a single Jupyter notebook, as well as a zip file of data. You can either clone the repository and run this locally. If you're interested in following along, I'll give you a minute to set up. You can click the Open in Colab or Launch in Binder. We're not going to be using any GPUs, so it shouldn't be an issue of resources. I've already gone ahead and opened this in Colab. And if you are planning to run it in Colab, just keep in mind that the system they might give you might be a little bit slow. So I recommend running through and going through the BART installation. This would be up to cell 8 while I'm talking, so that you give this a minute to run. You can see it takes about 2 minutes on this particular VM to run. Of course, you can also run it in Binder. It's loading right now, and you can run this locally. What I'm going to do for today is run it locally in my own host machine. So taking a step back, I wanted to talk a little bit about reproducible MRI reconstruction. I think we've seen really fantastic talks in this session on how to sort of democratize the whole acquisition reconstruction process, and there are a number of tools. And I think the most important piece is not which tool do you use, but more that all these tools can work together. So you sort of have the flexibility and freedom to choose the best tool for the job for you. So with that said, we've spent a bit of effort on trying to create a toolbox for MRI reconstruction that's both flexible, extensible for reproducible research, usable in clinical settings. And I'm going to talk a little bit about BART in more of a basic overview fashion. I want to mention that a lot of the material that I'll be talking about today is based on a similar presentation we gave in 2021 that was led by Martin Ucker, who's also the main developer of BART and his team, as well as some earlier webinars we gave in 2020, the first webinar that we held on BART when we had about 300 attendees. The BART website, which I hope you can see here, the URL, I'll go ahead and paste that in the chat, but you should be able to get to it as well. Sorry, there's a question if I can make the text a bit larger. I'll definitely do that. Thanks for the feedback there. And let me go ahead and monitor the chat while I go as well. Okay. This is the landing page for BART. We've put a little bit of effort to try to make it a little bit more organized. We're constantly trying to improve. We're working on a more extensible manual and documentation. But for now, you can read a little bit about the motivation, which again is about supporting reproducible research and reproducible pipelines, being able to work with high-dimensional data in a fast way, and also translating to the clinic. I think the most important link, though, is the tutorials page, which has links to all of our interactive notebooks as well as videos that go over various types of reconstruction pipelines with BART. So I encourage you to check that out. And again, we have both interactive notebooks as well as videos that you can watch. So with that said, I'd like to also mention a couple other landing pages. Under the MRI Recon GitHub family, we have the BART webinars repositories. Again, these are recordings plus interactive sessions, and there's a little bit of explanation if you go to the material on each one. And then we also historically have been keeping a parallel notebook called BART Workshop, where you can see a number of various workshop presentations that we've given at ISMRM as well as at MRI Together. So that's where we're gonna stay for the rest of today. I'll go ahead and switch to my Jupyter Notebook tab, and hopefully if you're following along, you've been able, say in Colab, you've been able to get BART installed and ready to go. Okay, so the purpose of this notebook is to introduce the BART toolbox and its use as a tool for reproducible research. The code for BART is open source, so anyone can inspect it, and it can be used to create reproducible notebooks that anyone can run given the same data. One quick announcement I wanted to make is that earlier today, we released BART version 0.9.00, and you can check the announcement on our mailing list. If you click right here, this will take you to the public-facing mailing list. It's open to the public, so anyone can read it without subscribing, but I also encourage you to subscribe. It's a place where people get help with BART, but also more broadly talk about MRI reconstruction best practices. But if we take a look a little bit at what has been released, the main message I want to give is that BART is continuing to develop with new features, and in particular, a lot of effort has been gone in this release to include more simulation tools, so making larger multi-coil phantoms with various types of geometry, as well as support for general parallel processing. So this is being able to loop over higher dimensions, run this on multi-cluster systems. But there are many other improvements that you can see. These are just the latest changes since version 0.8.00. Okay, so I encourage you to join the mailing list. And this is the general citation for the newest version of BART. So this talk, again, is a little bit geared toward beginners. And what I'm going to go over is how we simulate phantoms in K-space, and then how we reconstruct undersampled data from a particular scanner. Now, BART is really a series of command line interface tools as well as a C-based API. But I think for the most part, if you're using BART, you're probably using it for the built-in command line tools. And so in order to have an easy way to do that, after you install, you want to set up the paths correctly. So BART is supported on Mac, both Intel and ARM-based. It's supported on Linux, several distributions, and it's supported on Windows through the Windows subsystem for Linux. If it is a Linux-based system, then you can easily apt-get install BART, and on Mac, you can build from source. If you're building from source, then you want to set the toolbox path to the place where the BART directory was built. So if I install it in my home directory, I would want to change this directory to be my toolbox path. And this tells our system, after we export path, that this is where the BART binary lives. We'll be able to call it from anywhere we want. And the simplest way to interact with BART is through the command line interface. So this would mean opening up a terminal and typing BART commands. But we also include wrapper functions that allow use in MATLAB and in Python, and these are located under the MATLAB and Python directories. There's also been some work by others for making wrappers in other languages, and in particular, Julia also has a wrapper for using BART command line tools. And we definitely recommend running BART locally when possible. Only for demonstration purposes or for tinkering around, do we suggest using Binder and Google Colab, and the reason is that those are going to be significantly slower than running this locally for various reasons. But it's a good way to quickly get started. And if there's any, I'll just pause here for a quick check to see if anyone is following along and is stuck at this point. If you are running it on Colab and you finished installing this cell, what you should be able to see after running the next cell is that BART version will output the version of BART. This means BART was installed, and you can see that we're using the latest version as of this morning, version 0.9.00. But once again, for speed purposes, I'm going to switch back to my local setup. Okay, so this notebook has a little bit of extra glue to check if you're running it in Colab or not, if you're using GPUs, but in my case, these cells won't run because I already have BART installed and ready to go, and my environment is already set up. So when I check the version of BART, I get version 0.9.00. Okay, I'm going to show the use of BART today primarily through the Python interface, because again, I think it's important to recognize that people have various tools that they use, and we're not trying to say you should only use one tool. We want you to be able to use all the tools that are most flexible for you. So I'm going to use BART through the Python interface and combine it with some uses of NumPy as well. And here is a function that we can use just to make plots of the various items that we go through. There's also a zip file of some data that's included. So if you don't have that, go ahead and download it. I already have it downloaded and unzipped, so it's ready to go. It just has a case-based data set acquired on a 3T MRI scanner. Okay, so some of the basics. So BART provides a number of tools for image reconstruction and multi-dimensional array manipulation. And we can get a list of all of the available tools by running BART with no arguments. So in this cell, I'm going to run just BART. I have here an exclamation point because this tells Jupyter Notebook to run in Bash as opposed to the native Python kernel. So this is a trick to emulate running on the terminal. And if I run this, I can see the various functions or tools that BART includes. Some of the most common ones that we see people use is eCalib right here. This we'll touch on this later. And pix right here. And you can see that there's some generic options for looping over various dimensions. And that's one thing I want to emphasize is that even though BART's primary purpose is for MRI reconstruction, in a sense, it's a flexible multi-dimensional array backend. So how does it work? How do we call BART commands? Well, the commands are all structured in a similar way. They all live under the BART tool. You then give it the name of the specific command you want to run, whatever options are included, and then the input and output pairs. So each BART command consists of a number of optional arguments followed by these inputs and outputs. And if we want to get information about a particular command, we can include the -h flag. So for example, let's take a look at what the BART Phantom tool does. I'll call it from the command line for now, and I'll give it the -h. And this will give me the help string for the Phantom tool. So I can see that in order to use it, there are various optional arguments, many of them. These are all the ones in square brackets. And finally, there is a required argument, which is the output. It's going to be eventually a file name. And then below, we have information about what all of these various optional arguments mean. We can see we can pass it little s with a parameter nc, and this will make nc sensitivities as an example. We can give it -k, and it will produce a Phantom directly in Kspace. So in particular, we can see that the Phantom tool includes an option called -k for Kspace, and another one -x, which takes a single number n, and this will give us the dimensions in y and z, essentially the number of samples. Now, like I said, I'm going to focus on the Python interface today. So even though so far we ran BART through the command line, we're going to switch over to using Python. If you're running this in my binder, the paths are already set. And if you're running it in Colab, we're going to set them right now. If you're running it locally, then we suggest adding this to your bash RC, which exports the Python path. This tells Python to search in this directory, the toolbox path /Python, for any Python related modules, and in particular, we'll have the BART modules there. Okay, so once the Python path is updated, we can import the particular Python libraries. So we have two libraries that we'll focus on. One is the BART module, and one is the CFL module. Now, calling BART from Python has a very similar structure as calling it from the command line. because ultimately all we're doing is we're parsing the string of this BART function into a command line argument and then calling it on the command line. So how does it work? Well, whatever outputs you have, this would be a series of outputs depending on the number of arg out. We call the BART function. We tell it how many outputs to expect, a particular command with the optional flags, and then the outputs, the data files, or sorry, the inputs that we expect. Now we can also query the help string using the BART interface. I'll call a BART tool. I'll tell it, hey, it has 0 outputs because we're just calling the help string, and I'll call BART phantom-h again. So this gives me the same help string, but now calling it through the Python interface. Okay, so it looks like this phantom tool might be a useful tool for creating phantoms in image and case-based domain. Let's check it out. Let's use the phantom tool to create various types of phantoms. So here I'm going to make a Python NumPy array called BART phantom. I'm going to call BART. It expects 1 output, and I'm calling phantom with a -x of 256 and a $B. So let's go up to the help. We see -x, 256. This means that the phantom will have dimensions 256 in Y and Z. And there's also a $B. This creates the BART logo. I'm going to transpose it just for visualization, and then I'll call my BART plot function. I'm also going to make another array by calling the phantom tool. All I'm doing is adding a -k to the end, which, as we saw before, adds a k-space argument. So it creates the phantom in k-space. So, and then I'll call BART plot again. Okay, so we called BART, we plotted the phantom tool, and this gave us this BART logo. So this is a phantom that we've created in the BART program that creates the BART logo. This is in image space, and this is in k-space. And just give me a second. I recognize that I have my debug level set really high, which is something I use for development, but I don't want to do it in this case. So just bear with me 1 second. I'm just going to reopen my Jupyter notebook. Instance just to set an environment variable so that we don't get really annoying help strings. Yeah. All right, we're back where we were. All right, here we go. Created a phantom. Okay. So this is the BART logo in k-space. Okay, so how does the actual BART file format work and metadata? Well, usually we're thinking of BART on the command line, and BART data files are typically stored as 2 files on your computer, a header file, which has the HDR extension, and this has metadata about the particular file, like what are the dimensions, what is the file type, what created the command, as well as a .cfl, which stands for complex float. And that's the actual raw data. So the header file is just a text file, and it can be opened with any text editor, while the raw file is binary. And the raw data is a multidimensional array of single precision complex floats stored in row major order with interleave real and imaginary. What does that mean? It means that if you have your own raw data from your vendor neutral scan, as long as you can write it as a binary file where you interleave the real and imaginary, this should be column major. As long as you store it in the particular order, then you can read it into BART. Now, I do want to mention a caveat when using the Python and MATLAB interfaces, which is that in the purest sense, we're not actually loading, interacting with these through Python directly, but in fact, what we're doing is we're not storing it in RAM, but every time we call the Python binding, we're writing the file to, we're writing the NumPy array to a file on disk, and then calling the command in the command line and then reading. And so that could be slow. So if you're actually using BART in Python for an important application, we recommend making a RAM disk so that you're actually running it on RAM. Now, the Python library that we imported called CFL has some helpful tools for saving and loading data in NumPy compatible format. So in particular, we could create a complex float array in NumPy and then load it into BART from the command line, or we could create a BART file from the command line and load it into Python. So for example, I could create a NumPy array, call it capital A with some complex numbers in it, and I can call the write_cfl function to write this to a file called A, and it will create two files. It will create a.cfl and a.hdr. And then I can use the show command of BART to look at the values of that particular BART file. So here I'm just listing the files in my directory that are a.something, and I can see here these two particular files. And when I call BART show, I can see that it has the values that I created in NumPy. We can do the opposite. So I could create a file using the BART function. In this case, I'm going to make an all ones array with 2 dimensions of size 3 by 3. And then I'm going to read the file into NumPy. And so here I made a 3 by 3 array. It's a NumPy complex float. It has all values of 1, no imaginary component. Now, because the header file is a text file, I can also just directly print it. So I can use bash and just look at the input of the text file. And we can see that it tells us the dimensions of the file, 3 by 3, the command that created the file, and the particular dependencies and what version of BART was used. So this is a useful way of tracking how these BART files came to be. Now, I'm not going to discuss it here, but BART can also write other file formats that might not have a text header as a separate file. And so it's typically better to use the API for the show command. For example, if I want to see what are the dimensions of this B array, I could do BART show -m. And we can see that it tells me, hey, it's a complex float. It has a whopping 16 dimensions. And the size of these dimensions are 3 by 3 by 1 by 1 by 1 by 1 by 1, right? So in fact, our data is 16-dimensional internally, but only the first 2 dimensions are non-singleton. All the others are all ones. In essence, BART supports up to 16-dimensional arrays. So far we haven't seen anything that requires that many dimensions, but it could. And if some of them are singleton dimensions, then they won't really interfere when we load them. By convention, though, when we're dealing with MRI data in particular, we've come up with some standard where the first 3 dimensions represent spatial dimensions. The next dimension is the coil dimension in multi-coil MRI. The next dimension is related to a second set of sensitivity maps for soft sense reconstruction. And then we have higher dimensions like echo times and coefficient dimensions and other higher order dimensions, like sometimes we might use them as a standard for flow encoding or for phases, etc. When using the Python interface, though, just keep in mind that the higher order singleton dimensions will be squeezed out, and so you might not see it as a 16-dimensional array because it only has the first 2 leading dimensions as non-singleton. Now, the real power of, I think, the BART tools is that they all work on these 16-dimensional arrays in a really flexible way. We don't have to write any for loops in order to operate on them. So I realize I'm already a little bit stretched for time, so I'm going to go through this a little bit and then show some of the main demo, which, again, you can run on your own. But let's say that I wanted to reconstruct the BART case space phantom using the IFFT. Well, there's an FFT command that we can look at the help string of. So FFT, there's some optional arguments, a required argument called bitmask, an input file, and an output file. Let's check the shape of our BART phantom real quick. So this is the phantom in case space. It's 256 by 256. And now I'll use the FFT function with the -i flag, which specifies inverse. And I'm going to give it this magic number 3 and the particular input. Let's do that. And we get the IFFT of the BART case space phantom. So we performed an inverse FFT, and we performed it on dimension 0, 1 specified by the bit mask 3. So what does this bit mask mean? The bit mask essentially allows us to choose what dimensions we want our tool to operate on. And this is a really flexible approach that we use in all of our commands, in many of our commands. In essence, what we wanted to do was an IFFT along the dimension 0 and dimension 1. And this corresponds to the bit mask 2 to the 0 plus 2 to the 1, which equals 3. If I wanted to do it only on dimension 1, I would give it the bit mask 2 to the power 1 or 2. And we can calculate bit masks very easily for specific dimensions using the bit mask tool. So if I want to do bit mask 0 and 1, it tells me it's dimension 3. If I also wanted to do an FFT along dimension 10, I need to give it this particular bit mask. So this is a good way of doing multi-dimensional array processing without explicitly writing for loops. Let's quickly compare the reconstructed BART phantom to the original image domain phantom. So I have my BART phantom that I created in the image domain. I have the BART phantom that was an IFFT reconstruction of the K-space. I'm going to calculate the error, and I'm going to just make an image that shows all three together: the image domain phantom, the K-space reconstruction, and the error. Okay, so maybe a question for the audience at home is, why are these two images not identical? And in the interest of time, I'll just go ahead and answer the question, but this is really demonstrating something called the inverse crime, which is that creating a phantom directly in image domain and then taking the DFT is different than sampling a continuous function in Fourier space and then taking the IFFT. And so we can see essentially we've lost some edge information corresponding to ringing artifacts by sampling the BART phantom in K-space followed by IFFT, compared to just a discretized version in image domain. Okay, so there's two examples that I wanted to get through. The first is building a multi-coil phantom using the BART simulation framework. And the second is actually reconstructing raw data in the data.zip. So we can create a synthetic K-space phantom in K-space directly, and this time the Shep Logan. We can make it multi-coil. We can undersample it with a USAMP tool, UPAT tool, and then we can create sensitivity maps for a sense-like reconstruction and followed by parallel imaging reconstruction. So here I create a phantom in K-space directly with 8 coils and a 256 number of samples. And so I have an array of size 256, 256 by 1 by 8. The 1 is because this is a 2D data set, so the third dimension is 1, and it has 8 coils. And here are the nice K-space channels. Next, I'll create a subsampling pattern. I'm not going to talk about what I'm doing here, but the purpose of this is not to show the best way to create a pattern. It's actually to give you a chance to see how I use BART tools and chain them together to create something richer. So I'm going to make a sampling pattern with an auto calibration size of 20 and a phase acceleration of 2 using only BART commands. But again, there are better ways of creating this if you care about efficiency. But here's my sampling pattern. I could also change the phase acceleration to 4, and I'll get a 4x acceleration pattern. But let's stick with 2 for now. Let's go ahead and multiply, and now I'm going to use some NumPy tricks, right? So broadcasting. So I'm mixing BART and NumPy, and now I've undersampled my Shep Logan phantom in K-space. Let's do an IFFT and root sum of squares reconstruction. So I'll call the FFT tool followed by RSS, specifying the bit mask I want to do the root sum of squares on, and I get my root sum of squares reconstruction, which has obvious aliasing from the undersample. Okay, let's try a more advanced method. Let's use the eCalib tool to create sensitivity maps and then do a sense reconstruction. So I'll use the eCalib tool. I encourage you to check the main options on your own, but one thing in particular is we're going to do a classic sense-like reconstruction, so I don't need soft sense maps. I'll just use eCalib-M1, and here are my 8 sensitivity maps. Given the sensitivities, we can use the PIX tool, which stands for Parallel Imaging and Compressed Sensing, to do an iterative parallel imaging reconstruction. It's a very generic tool that essentially solves this regularized least squares problem with a lot of flexibility on what the regularization terms are and what the forward model is. But we're going to use it in one of the more generic ways by using an L2 regularization in which case we're just doing sense, and we'll be using the conjugate gradient algorithm under the hood. So I'll specify a lambda parameter for the regularization factor and a number of iterations, and then I will call pix using the Python interface to get my CG sense reconstruction. So there we go. This is a reconstruction from undersampled data created in K-space. You can see the ringing artifacts, but we get a nice result because of the multiple coils. And so we can combine this and take a look at the root sum of squares versus the CG sense. Okay, the next little piece that I want to go through is reconstructing data directly from scanner data. And again, because the BART file format is simple, it's possible to read data from many sources. In particular, BART internally has a Twix read tool for directly reading Siemens data. And we also have on our website a GE Orchestra library, which lets you directly read P-file and scan archives. But again, you can create any reader as long as you interleave the binary file correctly for the real and imaginary complex foots. So in this data folder, though, I have a K-space data file, I have a ref file, which is the auto-calibration reference scan, and I have a noise pre-scan that we'll use for all three for the reconstruction. So I can call BART show on each of these and see the dimensions. K-space is 768 by 382 by 1 by 16. The ref scan is 768 by 33 by 1 by 16. And the noise pre-scan is 768 by 1 by 1 by 16. So 16 coils. I load them into Python with my CFL library. Now I have NumPy arrays corresponding to them, and I can also plot them. So here is the reference data, and here is the K-space data, which is directly undersampled. Maybe make the window a little bit higher to see. So based on these array sizes, we could infer that the reference scan has 33 phase encodes, and that our scanner automatically doubled the field of view in the readout dimension. So as first steps, let's just crop the readout dimension to field of view over 2 and zero pad the reference data to be the same size in the phase encode dimension as our K-space data, and take a look at that. So now we have our reference scan, the low resolution image, and we have our coil images, which are undersampled. Now, I want to encourage, when you're working with real data, remember that it's noisy, and if it's multi-coil, it may not be the case that the channels all have equal variance. And so I encourage you to do noise pre-whitening. Now, there's a really good tutorial on image reconstruction pipeline by Michael Hansen, and he talks about noise pre-whitening. And we've implemented a BART whiten tool, which will inspect the covariance matrix and create a noise pre-whitening matrix. So you can take a look at the options of the whiten tool, but I'll go ahead and run it. And we can see the noise covariance matrix of our 16 by 16 channels before pre-whitening. So there's various values of the variance and covariance elements. And then after pre-whitening, we have a nice uniform identity covariance matrix. So now we'll work with the noise whitened data from now on. Remember, we have 16 coils, and that's a lot for computation. So we'll use the CC tool, the BART CC tool, to coil compress. And I will coil compress using the reference ACS data and apply it to the K-space data. So I run that, and now I've coil compressed to 8 coils, so it's a little bit more manageable computationally. And we can look at the RSS reconstructions. So here's our RSS of the reference ACS data and the RSS of our subsample data. So this data is already subsampled. I can run coil sensitivity estimation just like before. I'll run it on the reference ACS data that has been whitened and coil compressed and zero padded. And I get my 8 sensitivity maps. And they look this way because they're coil compressed sensitivity maps. Finally, I'll run parallel imaging and compressed sensing tool with L2 regularization. So this corresponds to a CG sense. One detail is that I want to normalize the data before running the PIX command. And because the reference data is separate from the actual data, I want to calculate that myself. So I get a scale factor of 105. This will help me choose an appropriate regularization. And now I will run the reconstruction, conjugate gradient algorithm. Took less than a second. And we get our final result, which is the parallel imaging reconstruction of our subsample data after noise whitening and coil compressing. And now I have this nice artifact, this notebook that can be run by anybody and produce the same result, as well as tracking which version of BART created it. And so that's a nice way to showcase, I think, your research as you publish papers. I think releasing code is a really important way of allowing other users to get closer to reproducing the results of that paper. So I'll stop there and just again want to emphasize that we have many other demos, including videos and interactive notebooks that showcase many different BART features, all the way from basic compressed sensing to machine learning reconstructions on non-Cartesian, multi-dimensional data. So take a look if you're interested to learn more. Thank you very much.